Hey, Barack. Joe, are you there doing some math and I'm trying to learn a really cool theorem relating to modules called the structure theorem?
I'm here, Trump.
What's up, man?
So basically, here is what the theorem says. Let M be a finitely generated module over a Euclidean domain R. Then M is isomorphic to R quotient the ideal generated by D1. Direct sum all the way up to R quotient by the ideal generated by DT. Direct sum with K copies of R. For sum D1 up to DT with D1 dividing D2 up dividing dividing DT. And some integer K greater than 0. The DIs are called invariant factors.
That is a pretty cool theorem, Jack.
So true. This is probably the best theorem in the history of theorems, maybe ever. One problem, though, I'm not sure how to prove it.
I think I can help with that, Donald. So here's the idea. First, I will prove a lemma. This lemma says that if M is finitely generated, there exists a surjective homomorphism from R into M for some N. Here's the proof of that. M is a finitely generated or module sum equals or M1 plus dot plus or Mn for some N. Define F from Aaron to M by the tuple or 1 up to Aaron goes to the sum over of M I and I. It is pretty straightforward to show this is surjective and a homomorphism. Now back to the main theorem. Use that surjective homomorphism by the first isomorphism theorem. M is isomorphic to M over the kernel of the homomorphism. Now I'm going to prove another lemma at this point. We're a Euclidean domain. Any submodule of the free module Rm is generated by at most M elements. Here's the proof of that. Take some submodule and consider the set of R in R such that there is an M tuple in N with R the first element. This is an ideal of R since N is a submodally, so we get closure under addition and multiplication. Since Euclidean domains are principal ideal domains. Thank you, Joe, by the way, for making a cool video about that.
No problem, Barack.
We have that I is generated by a single element A in R. Let N be the tuple corresponding to A and N. Now, for any tuple in R, we have the first element of the tuple is our A for some R. Hence, the tuple subtract the tuple related to A gives another tuple with 0 as the first element. This gives another submodally N prime where all the first elements are 0. Apply induction to show that N prime is generated by elements. Now, and I know this is getting pretty long, we will use this lemma to prove a subtheorem to our theorem for our Euclidean domain. And is submodally of R to the M. There is a free basis x1 up to xm for M such that N is generated by d1x1 up to dtxt for some di in R. T less than or equal to M. And the d's dividing each other successively. We start by using that lemma we just proved to get N is Ry1 up to Ryn for some way I Rm. For some N less than M. We can then put these into a matrix A with columns corresponding to the Ys. Then put it into Smith normal form as A prime, which gives us invariant factors as we want. To put into Smith normal form, we apply elementary row and column operations. This converts the free basis of R into the free basis x1 up to xm that we want. And now that we have done that, we go back to the structure theorem proper. With that free basis, the kernel of the homomorphism is a submodule of R, which is generated by d1x1 up to dtxt with the divisibility property. Plugging this into the result from the first isomorphism theorem, we get the result.
Thank you, Obama. That really helps.
Yeah, Obama. That was a nice explanation. Also, this can be used to derive the fact that for G, a finitely generated abelian group, G is isomorphic to CD1 cross up to KDT cross C to the or with the divisibility property. This can later become the primary decomposition theorem.